Alright, good evening. Welcome to our video on length contraction. The syllabus is asking us to do three things here. Firstly, we need to recall the consequences of the constant speed of light in a vacuum, in this case meaning length contraction. We need to define a couple of words: length contraction, proper length, and relativistic length. And finally, we need to be able to describe length contraction and some examples of evidence that relate to this. So let's start off with the first part, in that we are recalling the definition. Now, the definition for it here is a reasonably straightforward one, and the textbook does go through it. There is a very long, complicated one. However, we don't want to use that in the syllabus. We're going to just refer to a shorter one here. Now, as we went through in class and we talked about with, what's what I'm looking for, and it is covered here in the textbook a bit, is the idea of using relative motion and frames of reference. So let's have a think about someone travelling between here and another star. So we have Earth, we have our spaceship, we have another star, Rigel for example, and we have our spaceship. Can't draw, obviously. There are two frames of reference happening here. For the frame of reference of a person sitting here on Earth, Rigel's not moving away from Earth. Let's ignore expansion of the universe. But these two things are stationary, and so to me on Earth, the spaceship is moving away. However, in the frame of view of somebody sitting on the spaceship, well, the spaceship's not moving relative to him. However, the Earth is moving away and Rigel is moving towards him. So there are these two frames of reference here. Now, we talked about time and proper time, and we derived this equation that t equals t naught multiplied by, divided by the square root of 1 minus v squared over c squared. And that, well, if we have some value of time and we, what's the word I'm looking for, as we go faster and faster than the speed of light, then closer to the speed of light, not faster than the speed of light, sorry, having a bit of a stupid day. As we get close to the speed of light, then our time that we see from an outside observer will change in response to that. Now, if we take this and we think about the motion here, that means, well, this distance that's being travelled, there would be a length and a proper length. And the question then is, well, what would happen to the length as it relates to this? Now, let's rearrange this equation for a second. T naught is our proper time, the time experienced by the object moving. So we're going to say that T naught equals T square root 1 minus v squared over c squared. That's just a rearrangement of that. And we know that if we measure the distance that this thing is going, because the one thing that they can agree between them is that their velocities are the same. Right? This guy's seeing this thing travel off at whatever percent the speed of light, but he and he are seeing the Earth go backwards and Rigel come towards it at the same percent of the speed of light. The direction is different, but the magnitude is the same. So we can say that the v for this person, or the magnitude of v for this person, equals the magnitude of v for this person. And we have talked about here, well, we have its velocity. Velocity is displacement divided by time. So velocity, or length in this case, is equal to velocity multiplied by time. We rearrange that equation. Velocity equals displacement divided by time. We did that at the start of this year. Okay, so now let's give our lengths here some references. Now, this guy here, this is not moving relative to him, so he knows how far that is away from him. We're going to say that this distance for our Earth observer equals L naught. Okay, so Earth Dude gets L naught, but we know he also has relativistic time, because to him, he's not going to see time go at the same speed that this gentleman will. In contrast, though, our spaceship will have proper time, because he will know how long that his time has gone on for. However, he will also have a relativistic length, because to him, he's going to be moving so fast that the length that this thing actually goes might not be as what's I'm looking for here, as how do we phrase this? Might not look the same as this original length. We're going to see if that happens. Okay, so if we go and take this person over here, let's see which one will we take. I will take this person here. We know that he's going at velocity, and we multiply by that time, then the L here should equal velocity times T naught. But we just saw that T naught equals this. So L equals velocity times time, square root 1 minus v squared over c squared. Now, we've got this Vt. Well, Vt in this case, we know that this thing has T, it's got the same V, so that must mean then that L equals L naught square root 1 minus v squared over c squared, or often this is sometimes written as L equals L naught over the gamma Lorentz contraction, the gamma function. Remember that the gamma function is 1 over square root 1 minus v squared over c squared. So in this case, it's because it's multiplied, it's over gamma. Now, what this tells us here, that if I make my speed of light high, and I have a fixed length, L naught, then my length is going to end up being smaller, because, let's have a look at this. V is always going to be smaller than c, so this number squared will always be less than 1. 1 takes some number less than 1 is going to be less than 1. Square root of that number less than 1 is going to be a small number, and then we're multiplying it by this. So in comparison to what we saw up here with time compared to proper time, where time got bigger, here relativistic length is getting smaller. So our gentleman here on Earth will see this ship get smaller, while our gentleman on the ship will see the distance between the planets get smaller. Both of them will experience a different perspective going on. And for some of these things you're asked, well, which is true, which is false? In this case, they are both true. He will see the ship get smaller, but the ship will see the distance between the two places get smaller. And this explains why muons will reach the surface of the Earth. Because muons have both this time dilation we've talked about and this length contraction, to them the distance from the upper atmosphere to the surface of the Earth is only a few hundred meters thick. They've got plenty of time to make it through at their speed, near speed of light. While if we only considered their time dilation, it didn't work quite well with the math. If we only considered the length contraction, it doesn't quite work with the math. We need to have a bit of both going on with it. Okay. So, let's go into a definition of what length contraction is. Length contraction. I'm just going to go for LC, quick abbreviation for myself here. So, length contraction is for anything. Okay, so length contraction is easiest way to explain it. What's the definition provided here? Yeah, there it is. Shorter observation made by an observer in the direction of motion. And what we mean by this is if I have my rocket ship and it is travelling this way, to a stationary observer it will look like this. It will have the same height still, and it would have the same width, however the length would be different. This would be length naught, proper length, and this would be the length of the observer. Okay. So, length contraction is this reduction in length. Length naught, proper length, proper equals measurement by stationary observer in that reference frame. So in the Earth, their stationary reference frame is the distance between the Earth and Rigel, so they have the proper length between Earth and Rigel. However, they don't have the proper length of the spaceship because they are moving relative to the spaceship. They're in a reference frame that is different. Someone standing on the spaceship would have the proper reference frame or the proper length of the spaceship itself. So even though we would see, and there's a very good video for this from Minute Physics, if something's going past you at a significant speed of light, you would see them getting shorter, or reduce their length. However, they would see you getting shorter or reducing your length. So both of these perspectives are true here. Alright, so we've had a look at the first bit, the consequence of it. In this case, yep, remember there's length contraction, we just need to know that this happens. And we've seen here a little bit of connection to the formula. There's nothing in the syllabus that you have to prove it. And remember, you have a data booklet, especially on an exam as well, so you could always go back to it. However, there's nothing there that you need to prove, at least from what I can see. You need to be able to describe it. Okay? We've gone through the definition, so you need to know length contraction, shorter length, proper length, the observer by the stationary observer, and relativistic length is a measurement of the, sorry, let's include that as well, relativistic equals the measurement by the moving observer. Okay. Sorry, my apologies. Measurement of the moving object by the stationary observer. Okay, so if I see that rocket go past, I am measuring its relativistic length. The person on the rocket ship is stationary relative to the rocket, so it measures the proper length, and would measure my relativistic length for me, because I would also be contracted to its perspective. That does rise an interesting paradox when we look at the ladder and the barn paradox, and we will discuss that in a later video. The last bit there is examples of experimental evidence of the phenomenon. Now, experimental evidence, for example, include things like particle colliders, where they should, and the muon phenomena, where they should vanish, however they don't. And so to them, one way of explaining the fact that they do reach the Earth's surface, or they do live long enough in the lab to reach a certain place, is that they are experiencing length contraction, that their length is significantly shorter than them, because they're travelling at anywhere from 0.6, 0.87, 0.9% of the speed of light. These things cause a contraction in length. Okay? So, in this we've covered the 3 parts of length contraction. We've covered our definitions, the words we need. We've talked about how we derive this equation. And then finally we have actually described the phenomena in a reasonable amount of detail. Remember, this is a descriptive term, cognitive verb. It is not an explanation cognitive verb. So even if you don't quite get it, what you just need to really consider is, well, how do we describe it? How do we solve some of the problems? And how do you hold on to it in your head for the couple of hours to get down on an exam? That's what you just got to focus on. Keep an eye on the eLearn. There will be some videos coming up about paradoxes that are reasonably important, and their animations are a lot better than anything I can do. So I'm just going to leave the paradoxes to be explained through the videos that I find. We've got one more to talk about, momentum to come next video. Thanks guys, have a good evening.